Okay. Thanks. Okay. So this is my first morning back at work after COVID and a week away without email. So I'll try not to be fuzzy, but I might be. Right. So most of my work revolves around understanding the ocean around Antarctica. And I guess the reason that we're interested in that is because Antarctica has been melting over the last few decades, and this melting is being driven by the ocean. Okay. So as you can see here, so the main areas on the last map you saw melting is like West Antarctica and some little bits on East Antarctica here. And so these are the same regions where we're getting ocean warming. And so the warm waters from the ocean come underneath the ice shelves and is melting the ice. And so the big questions in the field that sort of central to what I'm trying to study, what are the mechanisms that are controlling this ocean warming that we've been seeing over the last couple of decades? And as we look into the future, do we expect that warming to continue? And are there regional differences around Antarctica? So that's kind of the central science bit of what I'm trying to do. Okay, so some of the difficulties of trying to answer these questions, they seem like very simple questions, but there's a lot of detail in there. So this schematic in the middle here shows some of the processes that are important in terms of the ocean circulation around Antarctica and what we need to understand to figure out what the ocean temperature is doing. So I guess some of the main things, so we get the dense water formation around Antarctica. So we get heat loss to the atmosphere in polynyas. This forms dense water, which overflows down the slope and fills the abyss of the entire world ocean. We then have this warm water, which sits offshore. And for that to get up onto the shelf, there's no sort of simple mean geostrophic flow that occurs via. So it's all transient, small scale processes like eddies or tides or flows through canyons that you need small scales to model. Okay, so I've got some of these pictures here for you. Sorry, mind fog. Okay, so on the left here, so this is a polynya here you can see. So the winds blow off the coast, forming these small scale polynyas. Here's a picture of an overflow of a really high resolution simulation. You can see you can get complex mixing going on there in the overflow. This shows you kind of the scale of the eddies. This is the Weddell Sea. It's these really small scale eddies that are one of the main mechanisms that bring the heat up onto the shelf. The Antarctic slope current is this westward current that flows around the slope of Antarctica. Again, it's very narrow. And then there's, of course, sea ice processes that are important to determine the air-sea interaction. And you can see the scale of these sort of fractures and so on in this region here. And so to give you an idea of when we try to model these, how difficult it is. So these red boxes that I've drawn on here, I think they're the scale of a typical 1 degree climate model. And so you can see that none of these processes or features are captured by those scale of models. So we really need to get to higher resolution models in order to get the dynamics around Antarctica right to understand what's going to happen in the future. Okay, so most of my work at the moment that I'll be talking about today is based on ACCESS-OM 201, which is, I guess, the ocean sea ice component of ACCESS in a standalone configuration. So we use a 1/10 degree ocean and sea ice, and we force this with a JRA go-do atmospheric product. And so this is just showing you what it looks like. So this is observations on the left and the model on the right. So it gets sort of the right configuration. We get this warm region in West Antarctica on the continental shelf. Looks pretty good generally compared to a lot of other models out there. And one of the best things that this model can simulate compared to other models is this dense water formation up on the shelf. So a lot of models, particularly climate models, form dense water around Antarctica in these large open ocean polynyas that occur sort of in the middle of the Weddell Sea, somewhere out here, rather than up on the shelf in these 4 locations labelled here, which is where we see dense water forming in the observations. So we're quite happy with how the model's doing there. I'll talk a bit later about how we could improve it further. There's always room for more improvement. So to give you an idea of what these overflows look like, so this is a great visualization made by the NCI VisLab guys. And so this model was developed by COSIMA, which is a consortium of a whole bunch of universities in Australia, as well as CSIRO, the Bureau, Defence and AED, which is now on its second linkage program. And so that COSIMA has been behind the development of this model coupling SICE-5 and MOM5, and we're now moving forwards towards ACCESS-OM3, which will be a MOM6 and SICE-6 version. Okay, so I'm just going to go through briefly a few science projects using this model, just to give you an idea of the flavour of some of the science that we can do with these high resolution models. So this one project here, so we were asking the question of where does heat actually get up onto the continental shelf in Antarctica? And so I guess sort of the assumption in the field for a long time has been, so this is the sort of just controlled temperature, like pre-industrial temperature around Antarctica. You can see this West Antarctic region is quite warm. And so the assumption, I think, for a long time in the field has been that the heat transport across the continental slope towards Antarctica in West Antarctica is actually larger than elsewhere around Antarctica. But it hasn't really been quantified. And so we looked at this in ACCESS-OM201. And what we found, so this is a zoom in, so this is the same region we saw in the movie before. This is the Ross Sea, where there's these 3 overflows that come down from three troughs. And surprisingly, what we found that, so this plot here is showing where there's green, that's northward flow off the continental shelf, so that's these overflows. So you can see those 3 bumps correspond to these 3 overflows. And in the same regions, we get flow returning in the warm water layer above, this orange layer here, which is our warm water accessing the shelf. And we found that around the whole of Antarctica, this mechanism of this local return flow at the overflow locations actually dominates much more so than the heat transport in West Antarctica, which was quite a surprise. And so I guess the implication of that is that it's not so much the limiting factor of what determines the temperature on the shelf is not how much heat transport's getting across the shelf, but also the air-sea interaction once that warm water is on the shelf, how long can it stay there? Okay, yeah, so what we found instead so it's these 4 regions here where we get dense water accessing the shelf that dominates the total heat transport. Okay, so another example of a project. So this is looking at the temperature variability on the Western Antarctic Peninsula. So the blue region shaded on that map. And you can see, so I've removed the warming trend here. So there's a like 0.17 degree per decade warming trend that I've removed from that just to focus on this decadal scale variability. So you can see there's really large decadal scale of variability. So plus or minus half a degree, sort of on a 2-decade type scale. And so the model is this, just the line here, and the observations match quite well. That's the dashed line there. And again, something we weren't expecting here is if we plot the dense water formation in the Weddell Sea, which is upstream around the continent, we find that this matches very well. And so what we have found is going on here, we've done a whole bunch of experiments releasing passive traces and so on to look at the connectivity. We find that when we get years of strong dense water formation and dense waters exiting the shelf in the Weddell Sea upstream, we then get less connectivity around the continental shelf to the Western Antarctic Peninsula, and then we get warming there because you're not bringing the cold Weddell Sea waters around anymore. And the implication of this for the future is that if dense water formation slows down, there may actually be a negative feedback, some cooling on the Western Antarctic Peninsula. Okay, and then just onto the third and last example project. So this is a collaborative project with a whole host of amazing people. So what we've looked at here is how when we change winds around Antarctica, how does the ocean temperature respond? And so we think in the future that at least the CMIT models suggest that the winds around Antarctica are likely to weaken. Here we've just looked at an increase of the wind just as a kind of a simple thing to do, but we probably expect the reverse of this in the future. So a lot of people have focused on the zonal winds previously, because I guess the predominant winds around Antarctica are the easterlies. But if you actually look at the distribution of the winds, the meridional winds are actually quite important and strong as well. So what we find here, so if we look at the change in the zonal winds, so the easterlies, so this mechanism is sort of what we expected and what others have found before. So as you increase the westerlies, you get a southward increase in the Ekman transport, and this pushes down your density surfaces in the interior. And because you have cold waters on top of warm waters in the control, then as you push those density surfaces down, you get cooling most of the way around the continental shelf here. Much more surprising is the sort of the different temperature distribution response that you get when you change the meridional winds, the north-south winds. And so here what we found is actually the change in the bottom water, so the dense water production dominates. And again, you can see, so the 4 dense water formation regions here, the Weddell Sea, Ross Sea, and here, and it's downstream of each of these dense water formation regions that we're getting warming on the continental shelf. And so what happens here is we get, as we increase the winds, there's a sea ice feedback. So we get more northward sea ice transport, as this results in less sea ice over the continental shelf, which results in more dense water formation because you can cool the ocean more. And as you increase this overturning circulation here, then you bring on more heat transport from the open ocean, and it ends up warming on the shelf in these 4 locations. Yeah, quite interesting. So I guess sort of if I was going to summarize, I guess what we've found from all these studies, I guess it's that, so you really need to get these high resolution processes resolved in order to get this kind of dynamics. And also we need these sort of large scale models because these remote connections are really important. So things happening upstream are affected downstream around the continental shelf. Okay, so finally, how can we improve on this? So I guess we're looking at the moment to move towards MOM6, which has a number of advantages, which are mostly these ones down the bottom here. So I won't go into that in too much detail. It would be great to go to even higher resolution. So 1/10 degree is sort of barely starting to resolve the eddies on the continental shelf. So you really need to get to sort of a 20th or a 40th of a degree on the continental shelf to properly resolve the eddies there, because the Rossby radius gets small as you get that far south. This model as well doesn't have ice shelf cavities. And so there's a lot of circulation that we're missing. So there's sort of buoyancy pump. So if you release fresh water at depth within your ice shelf cavity, you get extra circulation that we're missing at the moment. So that's quite important. We'd like to include that. And MOM6 allows us to include ice shelf cavities once we move towards MOM6. Also tides. So tides are thought to be important for sloshing water back and forth across the continental shelf, which after mixing can leave heat on the shelf. So yep, at the moment we have no tides. And we'd also like to move towards having an improved vertical coordinate. So at the moment we just have basically sort of flat layers in the ocean model, and that results in spurious mixing, too much mixing, particularly as those dense waters overflow the continental shelf. Cool, I think that's all I have. Yeah, thanks.
Thank you, Anna.
Yes.
I think we may have the time for one question. May I remind people in the room to introduce themselves when they are on the microphone? Other people online. Any questions? Dietmar?
Yeah, I'm Dietmar from Monash University. How high resolution do you need in the atmosphere to simulate these kind of things? So
yeah, so I guess at the moment, so this is not coupled.
Yeah, but instead of forcing, so what
I guess the most important thing is the katabatic winds. So I guess I've compared higher resolution atmospheric products with so the JRA GoGo Do is 0.5 degree. And that seems to be fairly good. I mean, it's a reanalysis, so I guess maybe it's representing higher resolution processes into that.
But 0.5 degree is much coarser than what you simulate in the ocean, right? So you don't need
Yes.
similar resolution in the atmosphere.
No, I don't think so.
Okay,